We want to find the relation between vertex cover and independent set. With example, let's try to understand this. Tell me, if I have this example, A, B, C, D, E, F. So let's assume this is your example. Can anyone give me the can anyone give me a vertex cover? Give me a vertex cover. Any vertex cover. Give me a vertex cover. Whatever vertex cover you want, you can give me. Give me a vertex cover which will cover all the edges. So I can say, I can take this vertex cover. I can take A comma B. Okay. I can take A comma B comma D. So I can take A comma B comma D and F. A comma A B D F. So this is what I can take. Okay. This is your vertex cover. Now tell me, very interesting thing. See, very interesting thing. Now you can notice the remaining vertices, what they will create. The remaining vertices, what they will create. Very interesting thing. The remaining vertices, what they will create. The remaining vertices means the complement, the remaining vertices. The remaining vertices means C comma E. These are the, what they will create. They will create an independent set, right? Yes or no? They will create an independent set, correct? Are you getting my point? So this is the interesting thing. This is what I'm saying. So the remaining things will create an independent set. Now, what I'm saying, this is the claim. This is the claim. If you have a vertex cover, okay, so let's assume you have a graph G, V, comma, E. This is your graph. You know, this is your graph. Let us assume that S, which is subset of V, right? Let us assume S is a vertex cover. Let's assume this is vertex cover. Then what will happen? Then V minus S is independent set. Is independent set. Are you getting my point? So like here, this is the vertex cover. This is the vertex cover. And the remaining vertices, V minus S, this is S. So V minus S, that is your independent set. You can take, for example, you can take this vertex cover. Let's take this vertex cover S. What is this? Let me take this vertex cover. Like I can take B. If I take B, then this will be covered. Then I can take C. Okay. Then I can take C. So this B comma C, they will cover. And then I can take E, F. This is also vertex cover. Yes or no? Is this vertex cover? B, C, F. Are we covering all the edges? Yes, we are covering all the edges. What? Okay, the remaining vertices S complement. What is the S complement? The remaining vertices means A comma BCF, right? BCF. So that will be ADE. This is what? This is independent set. Are you getting this point? This is independent set. This is interesting. So this is what I'm saying. If your vertex cover you have, then the complement will be independent set and vice versa. And vice versa. The same thing will happen if you have, for example, if S is independent set. If S is independent set, then what will be V minus S? If S is independent set, if S is independent set, then V minus S is vertex cover. Then that is a vertex cover. Then that will cover all the edges. V minus S will cover all the edges. And the proof is actually very cute proof. The proof is like this. See the very cute proof. What you do? Let's do this. So this is your graph, G, V, comma, E. This is your graph. And let us assume that S is vertex cover. Let us assume S is a subset of V. And let us assume this is your vertex cover. Let's assume this is the vertex cover. If this is the vertex cover, then what? Just look at this. Let's assume this is your V. This is your V. And this is your vertex cover. Let's assume this is your S. This part is S. So this part is basically S. Now this means this is a vertex cover, right? Remember, this is all the vertices. And what is this part? Can anyone tell me what is this part? This part is V minus S. Now notice that if this is your S, means if this is vertex cover. If this is vertex cover, is it possible that there is some edge here? Is it possible? Please tell me. If this is vertex cover, if this is vertex cover, is it possible that there is some edge here? Is it possible? Why it is not possible? Why it is not possible? Like this edge, is it possible? Do we have any edge here? Why this is not possible? Because vertex cover should cover all the edges. Array, this is vertex cover, so this should cover all the edges. This should cover all the edges. Yes or no? This should cover all edges. All edges must be covered by this. All edges. Every edge must be covered by this. But this edge is, so this is not possible. I can say this is not possible. There is no edge here. Yes or no? Because this vertex cover should cover all the edges. This should cover all the edges. So I can say this edge is not possible. In this area, there is no edge in this area. But this is fine, right? This is fine. Yes or no? Is this fine? Like one vertex here, one vertex here. This is fine. There is no problem. Okay, so this is fine. There is no problem here. But you cannot have this edge because this edge is not covered by the vertex cover. So this edge is not possible. Very simple point. So finally, what I can say, if there is no edge here, so this is your vertex cover, I can say that this is your, this S, this is your vertex cover. Then what can I say about this area? Then what can I say about this area, V minus S? These vertices, what can I say about these vertices? Are they adjacent or not? Are they non-adjacent? What can I say about these vertices? They are non-adjacent, right? These vertices are non-adjacent. These vertices, they are non-adjacent because they don't have edge. These vertices, they don't have edge. Yes or no? They cannot have edge. This type of edge can be there, no problem. This type of edge can be there. This type of thing can be there, no problem. All the edges are like this. All the edges are like this. But I can say that this area, look at this area. Look at these vertices. Look at these vertices. These vertices are not adjacent. Yes or no? These vertices are not adjacent. This edge cannot be there. So these area, these vertices, they are not adjacent. So this V minus S, this is a independent set. Did you understand this proof? Very simple, very cute proof. Yes or no? Like very simple proof. We are just using the definition. Just using the definition of vertex cover and using the definition of independent set. Very simple proof. So if this is your vertex cover, then this will be your independent set. The same thing, let me do for this. If this is independent set, so again you have a graph. In this graph G, V, G, this is your graph G, V, comma, E. Let us assume that, let us assume S. Okay, let's assume this is independent set. Let's assume this is independent set. So this S is independent set. This is the point. This area S. Now this is your independent set. These vertices are the independent set, means these vertices. Okay, these vertices are the independent set. And these vertices, what these vertices? These vertices are V minus S. Now tell me one thing. Tell me one thing. Do we have any edge here? Do we have any edge here? These vertices are independent set. So we don't have any edge here. So where are all the edges? Where are all the edges? Just ask this question. Where are all the edges? All the edges are like this. All the edges must be like this. Here you cannot have edge. This edge is not possible. This edge is not possible. Like this edge. Look at this edge. This edge is not possible because this is independent set. This area is the independent set. So this edge is not possible. So all the edges, where are all the edges? All the edges are like this. So what can I say about this area, V minus S area? Is it covering all the edges? Is this covering all the edges? This V minus S area, this area, this V minus S area, this is covering all the edges, right? This is covering all the edges. Is this clear? Because all the edges are like this. Where are all the edges? All the edges are like this. So all the edges are covered. This area is covering, this V minus S is covering all the edges, because there is no edge here. We don't have any edge here because this is independent set. So I can say V minus S is the vertex cover. So I can say this will be the vertex cover. So this is what we have seen. We have seen that this is the node. What is the node? If you take any vertex cover, then the remaining vertices will be the edge independent set. See, this proof is like very cute proof, very simple proof. This proof, very simple. So this is the idea. If you have a graph G, if you have a graph G, V, comma E, then what we are saying, then for this graph, I can say that if S is independent set, if S is an independent set and S is subset of V, S must be because independent set I am talking about. Okay, so if S is independent set, let S be subset of V. Now these are the 2 points, or there is 1 point basically. S is independent set if and only if S is independent set, then what it means? It means V minus S is what? Tell me, V minus S is what? That is vertex cover. And if this is vertex cover, then S will be independent set. So there is if and only if here. If S is independent set, then V minus S will be vertex cover. And if V minus S is vertex cover, then S will be independent set. Very simple. Or the same thing I can say like this. If S is vertex cover, then V minus S is independent set. And if V minus S is independent set, then S is vertex cover. Very simple. Okay. This proof, is this clear? Very simple proof. Let me ask you one more question, and this is very simple question. This is your graph G, V, comma E, and let us assume that S is a subset of V. So means you have set of vertices. This is your set of vertices. Now tell me, if you know S is vertex cover, S is a vertex cover. If you know S is a vertex cover, then what can you say about, if you know S is a vertex cover, this S is a vertex cover, then what can you say about beta? What can you say about beta? Beta means vertex cover number. What can you say about beta? And beta is vertex cover number. If you already know S is a vertex cover, this is one of the vertex cover, then what can you say about beta? Can I say beta is equal to cardinality of S? Can I say? Beta means minimum vertex cover, size of minimum vertex cover. That is your beta. Beta is size of minimum vertex cover. Size of minimum vertex cover. So if you know S is vertex cover, then what can you say about beta? This beta will definitely be less than equal to this, yes or no? If this is already a vertex cover, then the minimum vertex cover will be less than this. S is already a vertex cover. So like in your hand, you have vertex cover. You already have a vertex cover in your hand. You already have this. Okay. So if you know that you have a vertex cover, then the minimum vertex cover should be less than this. Correct? Because this is minimum. So very simple. The same thing I can ask you for independent set. If you know that S is independent set, if you know this is independent set, then what can you say about alpha? What can you say about alpha? What can you say about alpha? Alpha means independence number. Means size of largest independent set. Tell me. If you already know that S is independent set, if you already know this, then the largest independent set should be greater than this, yes or no? Greater than or equal to this. Agree? Because you already know that this is your independent set. This is independent set. So the largest independent set should be greater than or equal to this. Very simple point. These are simple points I am asking. Okay, now let's see the relation between, now what we will see the relation between alpha comma beta. This relation we will see, where alpha is what? This is the largest independent, this is the independence number, this is the size of largest independent set. So this relation we need to see. Here remember, this is your independence number. This is your independence number. Independence number means size of largest independent set, largest. And you also know this beta, this is your size of, what is this? This is size of minimum vertex cover. This is the size of minimum vertex cover, or I can say this is your covering number, vertex covering number. Size of minimum vertex cover. Now let's see the relation between these two. So what will be that? Tell me one thing. If you know that this is your minimum, if you know this is, this you already know, let's assume that this is your largest vertex set. If this is your largest vertex set, this S, let's assume this is your this is your minimum vertex cover. Let us assume this is your minimum vertex cover. Let us assume. Then what can you say about V minus S? So this is your minimum vertex cover. S is your minimum vertex cover. Means the cardinality of S is what? Cardinality of S is what? Beta. Because I am assuming that S is minimum vertex cover. Then what can you say about V minus S? What can you say about V minus S? This is independent set. You can say that this is independent set. This is what you can say. You can say this is independent set, right? This V minus S is independent set. If this S is minimum vertex cover, ultimately this is a vertex cover, minimum or not. This is a vertex cover. S is a vertex cover. So V minus S is independent set. So the cardinality of S is beta. Then what can I say? This is your independent set. So tell me what will be alpha? The largest, this will be greater than equal to what? Remember, this is independent set. So the alpha should be greater than or equal to this. Yes or no? Are you getting my point? Because this is independent set. You have independent set in your hand. There is an independent set that you have. So the largest independent set, that should be greater than this. That should be, I can say that should be n minus beta. Alpha should be greater than or equal to n minus beta, where n is number of vertices. N is the number of vertices. So alpha will be greater than or equal to n minus beta. Very simple. The same thing you tell me, if this is your largest independent set, if this is your largest independent set, this is your largest independent set, the cardinality of V is n. You have n vertices. So if this is your largest independent set, then what is the size of S? This is your largest independent set. Then what is the size of S? That is alpha. Size of S, that is your alpha. What can you say about V minus S? This V minus S, this is a vertex cover. This is a vertex cover. So if this is a vertex cover, then what should be the size of minimum vertex cover? What should be the size of minimum vertex cover? This is your vertex cover. So what should be the size of minimum vertex cover? That should be less than or equal to n minus alpha. That should be less than or equal to n minus alpha. Correct? So finally, we have two equations. We have two equations. These two equations we have. Alpha is greater than or equal to n minus 1 beta. And beta is less than equal to n minus 1 alpha. These two equations we have. From this equation, I can say alpha plus beta is greater than or equal to n. From this equation, I can say alpha plus beta is less than equal to n. Then from these two, what can I say? From these two, what can I say? I can say alpha plus beta is equal to n. I can say this is equal to n. Very simple. Did you understand this proof? See this, like using this diagram, you can very easily understand. Using this diagram, we are just using the definition. Nothing else we are doing. Only using the definition. Also, this is a final point. Just understand this. This is the final point. If S is largest independent set, if S is largest independent set, then what will be V minus S? You know V minus S will be vertex cover. You know this. You know this will be vertex cover. But will this be minimum vertex cover? Will this be minimum vertex cover? Tell me. Will this be minimum vertex cover? You know that this will be vertex cover, but will this be minimum vertex cover? Will it be minimum vertex cover? Will it be minimum vertex cover? Yes, of course. Of course, it will be, because you know the equation. See, this is largest independent set. It means what? If this is largest independent set, it means what? This is equal to alpha. It means what? This is equal to alpha. Okay. This is equal to alpha. And you know, whatever is the minimum vertex cover, whatever is your minimum vertex cover. So what should be the size of minimum vertex cover? You just tell me this point. You just tell me this point. What will be size of minimum vertex cover? The size of minimum vertex cover should be n minus alpha. And what is the size of this v minus s? What is the size of v minus s? Size of v minus s is also n minus alpha. So yes, this is minimum vertex cover. No problem. Yes or no? Very simple point. See, S is largest independent set. It means the size of S is alpha. This is your largest independent set. Then the size of minimum vertex cover. The size of minimum vertex cover will be n minus 1 alpha, n minus alpha. This will be the size of minimum vertex cover. And this is a vertex cover, v minus s. This is a vertex cover. And its size is also n minus alpha. So this is a minimum vertex cover. So this is a minimum vertex cover. Very simple. So anyway, this is the point that largest, if S is largest independent set, if S is largest independent set, then V minus S will be minimum vertex cover. This will be minimum vertex cover. And the same thing will happen two-way. This will happen. Vice versa. Okay. So this is your topic. So we have seen this topic very carefully. We have seen the complete analysis we have done. This proof, did you understand this proof? And this is a GATE exam question actually. Everything that we have seen in today's class, there is a GATE exam question on everything. In the past, when you solve the previous year GATE questions, then you will see this question is there in the previous GATE. And the proof is actually very simple. Using this diagram, like these type of diagrams I am creating to tell you the proof. Did you understand the proof? Please tell me. Did you understand the proof? Did you understand?